Now, the next thing we are going to do is we are going to add these vertices as well as these edges. We're also going to set the edges. And we're going to execute this. Okay, this is what we get. Now, if you take a look at what we get, you'll notice that there's really no change in the printout from what it was before. And you'll notice that these additional vertices as well as edges do not show at all on our list. And that's because they are disconnected from our starting point. There is no pathway we can go from Abe to either Ham or Gab because these arrows are all pointing outward, and that is why they are not part of this list. But if we're doing a search, we want all vertices to be present in our list, even those that are not connected with our starting point. So we are going to amend our algorithm such that it includes all vertices. To include all vertices in our DFS search, what we will do is we will call DFS on all vertices and not just on VA. Okay. To do that, we already have created a list of vertices, and what we are going to do is we are going to call each vertex in that list. Now, we don't need to call this outside of the list anymore. Additionally, we need to add those two vertices we've just put within our list of vertices, and they are vgab and vham. And now we're going to execute our code. Now, if you take a look at these numbers, they don't look right. There's a 1, but there's no 2, 3, etc. And that's because when we call DFS on each vertex, it does try to process all of the vertices again. So what we're going to do is we are going to call DFS on all vertices, but we're going to make sure it only processes those that have not been processed. So we're going to say if and we're going to compare this with the graph. So what we see is we pretty much have the initial list, but we also now have Gab and Ham on the list. Now, Gab does have an adjacency on their list, and it's Eve. And you'd see for Gab, we visit Gab after we've visited Abe because we visit all the other nodes in the sequence they are on the vertexes list. And the visit time for Gab is 13. But when Gab looks into her list, the vertex finds that Eve has already been visited. Okay, so it's done processing and finishes at time 14, and then ham is visited at time unit 15, and then ham goes through the three uh, adjacencies on their list, and ham finds that they've all been visited. Okay, they've all been processed. So there's nothing else for ham to process, and it finishes as time step 16. And that's what's showing here. And based on this, you might have already noticed that if our starting point was different, we would have gone through this graph in a different way. For instance, if we had started at ham, we would have a very different structure. It would still be a valid search, a valid depth first search, but it would be based on depths from ham. Okay, so whether you get a, a single tree or a forest, which is a collection of trees, in fact, we have three separate trees in our search. All of these form a separate tree, and this is separate, and this is separate as well. Okay, and what you tend to find, okay, um, would be based on where you start your search from. Good. The next thing we're going to do is we're going to add the remaining edges, and those edges would be Eve to Dan. Those edges would be Eve to Dan, Flo to Eve, and Bob to Eve. And we run our code a final time, and this is what we get with all edges. Okay, let's compare our algorithm with the algorithm in the textbook. Okay, you notice some similarities. Here, they are using colors instead of the is processed we're using here. Now, they're using three colors: white, gray, and black. But you'd notice that they don't really check whether the color of a vertex is gray or black. They only check whether it's white or not white. And here's where the check is done. Okay, so we could have used something other than a binary value, but a binary value is sufficient since here they're using white and not white. Now, another difference you might notice is we are checking whether a vertex is a valid vertex. Now, this is a leftover from us starting off with binary trees. Now, because we are using an adjacency list representation, if we ever get to this point, we know it's a vertex. Okay, it's not a tree missing a particular left child or right child. Okay, so we can remove this without any consequence, and we're going to do that. Also, the only other difference is they are keeping predecessor information, which we can very easily do. And that is what we're going to do next. To keep predecessor information, we're going to have self dot predecessor is none, and within our DFS algorithm, we're gonna say neighbor predecessor is equal to vertex. Okay. Now we also spoke about the fact that if you get in here, it's a valid vertex because we are processing valid vertexes from adjacency lists. Okay, so this if is not needed, and if this if is no longer needed, we have to unindent since this is Python. And we are going to execute, and this is the same result that we got before.